In this video we're going to look at an example of using the CORDIC algorithm, and we're also going to look at it in the graphical calculator. Now I've written out the CORDIC algorithm here within the pink box. We're going to be using this diagram here, and we want to try and find the unknown angle, which is this angle here. Obviously when we're working through this example we know that the actual angle is 30 degrees. But you have to imagine for the moment that you don't know what that angle is. And all we have is this point here, which is the 0.866, 0.5. So we've got this point here and we want to find this angle theta. So we start with step 1 and we're going to be using the algorithm above. Now the value for k here for step 1 is going to be cos of theta 0. So theta 0 is just the angle which we're going to rotate the point by, and it's going to be an angle of 45 degrees. The value 1 is the value 1 here, and the value 1 is this value 1 here, and we're going to have minus d times 2 to the power of minus I. Well, I originally starts off at 0, so it's 2 to the minus 0, and we're going to have d 2 to the minus 0. And if we multiply that by our point x0, y0, which is this point here, we're going to get the new point x1, y1. Now, the direction of rotation of this point is dependent on the y value. So in the start of this, you can see that the y value is a positive value. So y is greater than 0. Now, if that was the case, you can see from the algorithm above, if y is positive, then the value for d is minus 1. So we can put that in here for d. So when d becomes minus 1 here, it becomes minus times minus makes it a positive. And the d minus here makes this a minus. So we end up with this algorithm here. Now if we were to multiply out this matrix, we're going to have 1 times x0, which is that one, and we're going to have 2 to the minus 0 times y0, which is that one. And that's going to equal the value of x1. And we're going to have minus 2 to the minus 0 times the value of x0, which is this term here. And we're going to have the 1 times y0, which is this term here. And that's equal to y1. Of course, it'll be all of this here times the cos of 45. But I haven't written that down in this instance. I just wanted to show you multiplying out this matrix. So let's go through the multiplication here, but we're going to kind of separate it a little bit. We're going to go through just the working out this term here, and after we've worked out these terms here, then we will multiply it by cos of 45, and we do that for a particular reason, and you'll see that whenever we look at the simulation in the graphical calculator. So we simply put our values in. x0 is going to be 0.866, and of course that's just approximate, so I'll put a better approximation to the actual value here. And the value for our y0, well, that's going to be the 2 to the minus 0 times y0. So 2 to the minus 0 is the same as 1 upon 2 to the 0. Anything raised to the power of 0 is just 1. So that's in effect just going to be 1 upon 1, which is a value of 1. So that's just going to be 1 times y0, so it's 1 times 0.5, which is 0.5. So whenever we add these two up, we're going to get this number here, 1.3660254. So I'll actually underline this because this is an important number for us. So we're going to have this number here, and then we're going to multiply this by our cos of 45. Okay, cos of 45 is 0.707, so we multiply this by 0.707 and we get this number here. So if we were doing a normal rotation, the value for our x would be this value here for our rotated point. Now we do the same in the second line here. We're going to have minus 2 to the minus 0, which is just a value of 1. So it's 1 and it's minus, so it's going to be minus 1. So it's minus 1 times x0, which is 0.866. So we get our minus 0.866 here, and it's plus y0, which is 0.5. So when we add these two together, we're going to get this number here. And again, I'll underline this number. And I'll give you a term here just in a moment, okay? So that's times the cos of 45. And when we multiply the cos of 45, we get this value here. So these two values here are actually the two that we're interested in, because whenever we work through this matrix here, you'll note that if the cos of 45 had been inside the matrix, then we would have a normal rotation. We would have one point in this circle here would rotate to another point in the circle. But that's not what we've got here. We've taken the cos of 45 out. So when we take the value of the cosine out of this matrix, we're going to change the rotation, meaning the style of the rotation is going to change. That is, we're going to have a rotation given by this section here, but we're also going to have a multiplication or a stretching given by this term here. So what we're going to have here is what we call a pseudo-rotation, and you'll see the pseudo-rotation just in a moment in the graphical calculator, and all this will become quite clear when we see those simulations. So now we still have to pull out our first angle that we have calculated. So we do that with the term here, z to the I plus 1, so it's this section here. So we're going to have z to the I plus 1 is equal to z to the I minus this term here, where this value e to the I is the arctan 2 to the minus I, so it's just a copy of what we have up here. So z to the power of I plus 1, well I is 0, so we're going to have z1 is equal to the value z0. Now z0 is the initial starting point, and we assume the starting point is just a value of 0. So we've got 0 and it's minus, and the value for d, well, d is going to be negative in this case here, because we've worked that out here. So it's going to be negative times negative 1, and it's minus, so minus minus 1, and it's e to the minus I, so e to the minus I is the arctan 2 to the minus I, so it's going to be arctan 2 to the minus 0. So that's going to be give us a value of 0, and this term here is going to give us a value of the inverse sine of the value 1 is a value of 45 degrees. So that's going to be in effect 0 plus 45 degrees, which is equal to 45 degrees. So our first stab at this angle here is 45 degrees. So let's go and have a wee look at this in the graphical calculator. So we have our circle here in blue, and we have our vector here in pink, and the point at the end is 0.866, 0.5, and we're trying to find this angle here. So this is our theta. Now we're going to start off by checking that the value y is positive, which it is, so therefore we're going to have to rotate this. So whenever we rotate it, now you'll see this rotation here, then I'll explain it after it's happened. So we're going to rotate it here, but you'll note here that a normal rotation would have taken this point here down to this point here. But what we're not creating a normal rotation, because we've taken the factor of cos theta out of the normal rotation matrix, and it's obviously going to change the rotation. So it's going to in effect split the rotation into two. There's going to be a rotation factor here, but there's also going to be a scaling factor, and the scaling factor is given by the factor that's taken out of the matrix, which is the cos theta value. So let's have a look at some of the points, and we'll relate the points to the values that we had in the example that we've just looked at. And once we've worked through our pseudo rotations, we would multiply the final answer by our value k, and our k would be our scaling factor, and all the value k would do, it would bring this point here and it would scale it and bring it back into this point here, which would then be a normal rotation. So let's see the rest of this example here, and we'll work through a second point. So we're now on the second step here. In this case, we've got the matrix, but the value for I is now the value of 1. So we're going to have 2 to the minus 1 and 2 to the minus 1. Now also, the value for y is going to be negative, and you can see that from our simulation, because now the value for y here was gone down to minus 0.366, so it's a negative value. So we take our matrix here and we multiply it for our new values, which are our x1, y1. So this is the pseudo-rotated point. So that's these points here, 1.366 minus 0.366, which we generated from the previous step. And that's going to give us the new points x2, y2. So we can write this out. If we were to multiply it out, we would have the value of 1 times the x1, so that's 1 there, and we're going to have minus d2 to the minus 1. Well, again, we know that y is less than 0, so d is positive. So that's just going to be minus 2 to the minus 1 times y1. And again here, the value for d is positive. So in that case here, this value is going to just be the 2 to the minus 1 times the x1. And then just the 1 times the y1. And that's going to give us a y2. So if we put our values in for these here, we're going to have x1 now, which is our 1.366. Minus 2 to the minus 1 times the y1, and this is going to give us the value 0.183127. So when we add those two together, we get this point here. And if we do the same for this line, we get these numbers here, and we get this figure here. So in effect, these points here are the pseudo-rotations. So this is going to be the next pseudo-rotated point. Now if we were to multiply that by our k factor, so the k factor now is going to be our cos theta 0 times cos theta 1. So it's going to be the cos of 45 times the cos of the second angle of a rotation, which is our 26.6. And that's going to give us the new point on the circle, which is this point. And if we do the same here, we've got this point here. So this is the pseudo-rotated point, and this is the normal rotated point. Now when we go to work out our angle, again, we're going to have the second, Z2 is going to equal Z1 minus D1 e to the 1. So now our Z1 we've already worked out is 45 degrees. We're going to be taking off, well, D1, well, D is just positive, so it's just going to be plus 1 times the E1, which is going to be arctan. In this case, it's 2 to the minus 1. So the arctan 2 to the minus 1 is a value of 26.6 degrees. So we're going to have our 45 minus 26.6 gives us our 18.4. So the 18.4 is the next approximation to our angle. So let's go ahead and we'll see this in the graphical calculator. So now we're going to rotate this point, but we're going to have to rotate it clockwise. And you'll see here, whenever we move it, you'll see that rotation happening. So now we're rotating it, but obviously, again, we're rotating it from this point here. So you would normally, we could draw a circle in for here all the way around, and this point would rotate round to a new point in the circle. But because we are performing this pseudo-rotation, we're going to get the rotation, and there's going to be that scaling as well. So that's going to shift us up by 26.6 degrees. So our next approximation to our value is actually the 18.4. So we've subtracted off the 45 degrees and we've added on the 18.4. So this point here is the new pseudo-rotated point, and you can compare this to the values that we looked at just in the last page. Now, if we were to then take this point and multiply it by our cos of 45 times the cos of 26.6, then this point here would actually shift on to the circle back to this point here, which would be our normal rotation. So this is a pseudo-rotated point, the point that we're actually using for the algorithm, and this would be the normal rotated point. So I've cleared everything off and set everything back to the original starting position. Now what I'm going to do now is work through all of the 9 approximations, and after we work through the 9 approximations, we'll go ahead and we'll add up all of the and subtract all of the angles to get our final value for the angle which we're trying to find, which is theta. So let's just work through these at the moment. So we're going to have our first shift, which is going to be a rotation by 45 degrees, and then we're going to have our, then we ask whether the y is positive or negative, so it's negative, so therefore we're going to have to rotate the next value, which is positive, in an anti-clockwise direction. And then again we ask the question, is the y value here positive or negative? The y value is positive, so we're going to have to rotate this in the clockwise direction. So you can see we rotate that to this point here. And again, if I zoom in now, and we get a finer and finer detail. So now it's negative, so we're going to have to rotate this point to this point here, and now we can see the value is positive, so we're going to have to rotate it to this point here, and you can see that the value is still positive, so we're going to have to rotate this point again, and now the value is negative, so we're going to have to rotate this point once more. And as we zoom in, you see we're getting closer and closer to the value for y is equal to 0. We can see the y height here is now positive, so we're going to have to rotate this. And we've rotated it, and the value is now negative, so the value for y is negative, so again we're going to have to rotate it in the positive direction. And you can see here at that point here, in this actual example, it turns out we land exactly on the y-axis. So what we've done here in this process is we've worked through the 9 iterations until eventually the y value tends towards 0. And in each iteration you can see we're performing a rotation, and also we're performing the scaling as well, because we've taken out that factor of cos theta out of the rotation matrix. But what we can do is we can finally at the very end, we can just multiply the final answer by the factor of k, and that factor of k would bring this point back in to this point here, which would be on the unit circle. So we've added and subtracted all of the angles that we get for each of the 9 iterations, and this gives exactly 30 degrees, which is the angle which we were trying to find. Now I've added a table here, and the last column of the table gives us the actual angles that we're going to be rotating in. So this is the 45, the 26.6, which is actually 26.565051. So these are the more accurate angles. So I suggest you go ahead and open up the file in the resources section, which gives you the simulation. And whenever you open it up, you'll see that you have the options down here in order to choose the rotation angles. So for example, we've started off with the example theta 1 is equal to 30. Now in this particular simulation it only works at 30 degrees. I haven't made it generalized for every angle, but you can leave theta 1 at 30 degrees and you can adjust these other angles. So this would be the first approximation, which would be adjusting it to this point here, and then this next approximation would adjust it to this point, and so on and so forth. And you can work through and have a little play with this, and you can also go in and have a look at each of the functions that we have in here if you're interested. And if you want to know how it works, you can always get back in contact with me. So this has covered a graphical simulation of an example of finding the inverse sine of a function using the CORDIC algorithm. Now we can also go ahead and we can look at working out the inverse cosine, so we'll have a look at that in the next video. So that's all for this video. Thank you for listening. I'll get you in the next video. Goodbye.